Hello there, we are in our fifth installment of section 2.5, and here we will be looking at the intersection between a line and a plane. Alright, so in finding the intersection between a line and a plane, we can assume that we have a plane and then a line would be intersecting it. Now, if we have a line and a plane in space, this is actually only one of the possibilities. There's a couple of other possibilities that we will entertain, and we'll take a look at them as examples. Okay, so how are we going to find the intersection between a line and a plane? When we think of intersection, we think of setting something equal to each other. Now, the forms that we're looking at, the parametric equation form of the line and the scalar form of the plane, does not really give a natural way to set things equal to each other. Well, but if we think about it, it kind of does, because when we think about the parametric equation of the line, we have an x value, a y value, and a z value, and those happen to be functions of t. So in terms of setting things equal to each other, I think the natural thing to do would be to replace your x value from your plane, your y value from your plane, and your z value from your plane with the x, y, z functions of t from your line. So for x, we will replace, in this example, for x we will replace this with 4 minus t, y is going to be 2 plus t, and then z is going to be 4t. And what we will have here is a linear equation in t, which can be easily solved for. So let's do that. We have 4 minus t minus 2 minus t minus 8t is equal to 8. That's a minus sign. And let's gather the t's together. There are, this is a plus 8t. If we gather the t's together, this is 8 minus t, so that's 6t. And then we have 4 minus 2, that's 2 on the left-hand side, and then we're going to bring it over to the right-hand side, so 8 minus 2 is going to be 6. So we have 6t is equal to 6, which means our t is equal to 1. So that is going to be our t value. Now, that is not the point of intersection, because we want the actual point. So the point can be given by putting the t back into this line. So let's put t is equal to 1 into that line, and we will get 4 minus 1, comma 2 plus 1, comma 4 times 1. So these are the values that you put in, and then you will get 3, comma 3, comma 4. Now, I know this is in vector form, but we want to look at this as a point, so we can write that as a point. So this is the point of intersection. Okay, let's view that in our handy dandy CalcPlot 3D plot. We have our line here, and I already have the plane typed in, and so that's the plane. And then if we look at 3, 3, 4, which is the point that we found, that is actually that point that we're looking at, and it is in fact on that plane and passes through that line. Now, another interesting view of this is that if we take a look at the trace for the line, you can see the trace, the vector tracer is this line, is vector coming from the origin to the line. So as we get closer and closer to 0, you can see it drawing out that line. And look at the t values here. T is equal to -1, t is equal to 0, and then t is equal to 1 will get you to that point. And then if you go past that, it'll go past that point. So what I wanted to illustrate here is that if t was equal to 1, then it'll get you to that actual point of intersection. Okay, so that's our first example. Let's take a look at another example. And here, this time, we have a line and a plane that looks like this. And let's see how we can work this out. So I think first we want to rewrite our line equation in terms of x, y, and z. So x is going to be 0 plus 1t. Y is going to be 0 minus t. And then z is going to be 2 plus 0t. So that's just a constant 2. Wow, that makes for fairly nice looking or easy looking line. And we'll put these values of x, y, and z into the plane, and then we will get x is equal to t plus y, which is negative t, plus z, which is going to be 2, and that's supposed to equal to 1. Now, this happens in linear equations way back when you were taking algebra and you were solving for equations like this. We have t minus t is 0, so this is going to be 2 is equal to 1. And we know that this is a contradiction. And so what is actually happening here? So the idea is that we were looking for an intersection between a line and a plane. So it looks like the plane and the line do not intersect. So that means the line must be actually parallel to the plane. So line is parallel to the plane. And we can verify that by taking the direction vector for the line. So let's say this line has a direction vector that looks like this. And then the plane has a normal vector that's perpendicular. And when we dot those, we should get 0. So let's just quickly do it since we're here. Anyways, we have the direction vector for the, or that was purple. We have the direction vector for the line is going to be 1, negative 1, 0. And the normal vector for the plane is going to be 1, 1, 1. And if we dot those two, so let's call this n. So if we dot n and d, we will get 1, 1, 1 dotted with 1, negative 1, 0. And that would be 1 minus 1 minus 0 plus 0. And that's equal to 0. So that does make sense. That does check out. And in this particular case, the line is not on the plane, and it's actually parallel to it. So there are no solutions. So line is parallel to the plane. We can just say no intersection. And one more example. In this example, we'll see another scenario pop up. So let's go through the process of solving for this again. We will let x equal to 1 plus t. We'll let y equal to 1 minus t. And we'll let z equal to 1 plus 0t. So that's our x, y, and z. We'll put all this stuff into the plane, and we will get 1 plus t for x, and 1 minus t for y, and 1 for z, and that's equal to 3. So if we combine like terms, the t's are canceled out, and we have 1 plus 1 plus 1, 3 equals 3. So that checks out, but I don't have a solution for t. So I think in this case, the solution is for all values of t, this will work regardless of what t is. This line and this plane will always be intersecting. So I think the scenario there is that your plane and your line, or let's say your line is actually on your plane. Maybe that was a little too much there. So let's just draw a line that's on the plane. Is on the plane. And now that the line is on the plane, it intersects at every single point on the line. All right. We didn't get to do a quick view of this. I actually have some graphs of both of these scenarios, Here is the graph of where the the line and the plane do not intersect. So here is the line, and here is the plane. And if we go look in one particular view, this is a view, it looks like it's parallel. And we can tell by zooming out more and more, the more we zoom out, the more we see that this line and this plane will never touch. All right, and then in our third example, we have a line. This is our line, and we have our plane, and we can see that the line is actually on the plane. You can see the line visible from below and above the plane. So no matter how we zoom in, it's always going to be on the plane. All right, so those are examples. Those are our graphics, and the simple process. You set them equal to each other, and I'll say that in quotes, and then you can say that you can find the intersection between the line and the plane. All right, good luck.